until after I got my master's degree. It would have been nice to do a little bit of that before I'd graduated. All right, so next week, it was the, let's just review here, the 13th is the STEM one. And I think that they'd like you to register for it on Handshake. Is that what your announcement that you got said? Register on Handshake for it? Pre-register? I mean, if you just showed up, I think they probably would let you in. But I think because of COVID, they probably are hoping to have maybe like managing the traffic and only a certain number of people at various times. All right, so class on Tuesday will be pre-recorded. Now I record all the class meetings and I do it on these little jump drives, which usually works good unless I forget to upload the lecture and then I lose the jump drive, which is what happened for Tuesday's class. I'm sure it'll pop up eventually, but earlier this week, the lecture that we had on Tuesday, I haven't uploaded it to YouTube yet because I can't find the jump drive. But last year's lecture is awfully similar to this year's lecture. So if you need to review the material where we just started talking about flow visualization and different flow types, so class number 13, you'll have to look at the lecture from 2020 until I find last Tuesday's lecture. So next week, our lecture will be online, but then the lab will be in person. And because we had A through K at 2 p.m., then next week, that A through K group, the first group would be at 3. It's the reverse. And then homework 5, which includes some problems from today's lecture, that is due on the 12th. Any announcement or schedule questions? All right. Remember that kind of the first part of the course so far was devoted to finding ways to predict pressure change due to a depth in a fluid. So the hydrostatic equation allowed you to model what the pressure would be based on the depth in the fluid. From here on out, the next few chapters of the textbook are devoted to predicting the pressure when the fluid is moving. And convective acceleration is one of the flow acceleration types that causes a change in pressure, and Euler's equation is what we can use to define how pressure changes when there's acceleration in one direction. I showed you a picture of a nozzle in class last time, and just briefly let's think about what's happening when you have a large diameter in the inlet of a nozzle and a small diameter at the outlet of a nozzle. And so here, the diameter at the inlet is such that the area is double the area at the outlet. And the way I know that the area is double in the inlet compared to the outlet is that the velocity increased. I haven't told you this yet, and in fact, we don't start talking about it in detail until chapter 5, but the flow rate is the cross-sectional area times the velocity. Maybe we talked about that a little bit in lab because we were calculating V is Q divided by area, but Q equals VA. And so the flow rate that's coming into this nozzle will be the same as the flow rate going out of the nozzle. Water is incompressible, so if you put 1 liter per second into the nozzle, then 1 liter per second has to go out. So what then that means is that if the cross-sectional area is big in the opening and small at the exit, then the velocity is going to have to increase to respond to that, because the flow rate in and out is the same, but if the area is low, the velocity goes up. So just because of the contracting shape of this nozzle, the velocity increases. And that is a non-uniform flow. Just to use the terminology that was introduced on Tuesday, non-uniform flow is where there's a change in velocity with respect to position. So as you flow from the left towards the right, the velocity is increasing. And it has nothing to do with the passage of time. It has to do with location in the flow field. So it's not unsteady flow that we're talking about. It's not that kind of acceleration. This is non-uniform flow that's caused by convective acceleration. So because of the taper in this shape, it's speeding up the liquid. The liquid enters at 10 meters per second, exits at 20. So therefore, there had to have been an acceleration. An acceleration is a change in velocity. And a change of velocity does occur here as the flow moves through the nozzle. Now what we know is what the velocity is as a function of its position inside of the nozzle. This is just an equation that applies to this particular nozzle. This isn't like a general equation that's always true. This just happens to be the equation that describes velocity with respect to position for this particular nozzle. So u is the velocity, and u naught is the initial velocity of 10 meters per second. And so what this says is that when the length is 0, like when your position x, when you're at the far left side, then the velocity is equal to the initial velocity. But then when x, you can see here at the top we're measuring x from the inlet towards the outlet. When x is the same distance as the overall segment length of the nozzle, then that means you're going to effectively be dividing the initial velocity by 0.5. So that means that then the velocity would be 20. So in the middle, it's going to be somewhere between 10 and 20 meters per second. And you can see that this shape, it's not a linear change in diameter. It looks like it's, kind of tapered a little bit. Like it's relatively parallel. The edges are parallel, but then they're coming together. As the edges are coming together, that's where the fluid is accelerating most dramatically. And then here at the end, where the edges of the pipe have flattened out and the diameter isn't changing anymore, the velocity is constant. It's where the diameter is changing most rapidly that the fluid acceleration occurs. And all of that's captured in this equation that relates the velocity at a position to the initial velocity. So this example is just to illustrate the process that we have to go through in order to find the convective acceleration. And we want to know it at a certain point. The convective acceleration is 0 at the inlet, and it's 0 at the outlet, because that's where those pipe walls are parallel. So the fluid velocity isn't changing as long as the pipe diameter isn't changing. But we want to know at the midpoint. So here, if the overall nozzle is 0.5 meters, so L is 0.5, I want to find out what is the convective acceleration here in the middle. And that appears to be where the acceleration is at its greatest. So where the distance from the left edge is 0.25. So does everybody understand kind of the background information and the setup of this example? We want to find out how rapidly is the velocity of the flow changing in the middle. Now, the definition of convective acceleration, A sub x means convective acceleration. Convective acceleration is, at a single point, it's the velocity at that location multiplied by the change in velocity with respect to position. So this is kind of interesting. It's different than local acceleration. If you think about what local acceleration is, A sub L, that's the change in velocity with respect to time, dv dt. What I'm saying here for convective is there's two terms for calculating the convective acceleration. The two terms are you have to know the velocity at that spot, and then multiply the velocity at that location by how the velocity is changing with respect to position at that location. And then you'll have units of meters per second squared. So let's go through this process of, first of all, finding the derivative of the velocity equation. Here's our velocity equation. So we want to find the derivative of that with respect to x. And then we will use the initial velocity to evaluate the function at the location we're interested in. All right, so velocity is, let me just write this on the whiteboard here. Velocity is the initial velocity divided by 1.0 minus 0.5x divided by L. I'm going to turn off the display here for a moment. We don't do calculus very much as civil engineers, but we're going to do a little bit of calculus today. What we know is that the length of this segment is 0.50 meters. The initial velocity is 10 meters per second. And we want to evaluate the convective acceleration at the midpoint, which is 0.25 meters from the left edge. So the definition of convective acceleration, a sub x, is the velocity multiplied by du dx. Now, you may recall the chain rule. And the chain rule says that du dx can be further broken down to the derivative of the function for velocity with respect to some intermediate term dm, and then multiplied by dm dx. And the reason why we need to do that is because we have an equation down here in the denominator, and what we're going to say is let m, this intermediate variable, be 1 minus 0.5x divided by L. So in other words, our velocity equation here becomes, the velocity is the initial velocity divided by m. So we're just taking the entire denominator and saying, let's make that a variable. In other words, that's like saying the velocity at a certain point is the initial velocity multiplied by m to the minus 1 power. Okay, so if that's the case, then du dx is d u naught times m to the minus 1 relative to dm multiplied by d, and let's actually substitute in the function here, 1 minus 0.5 x divided by L dx. All right, so that is, now if we take the derivative of this with respect to m, what that leaves us with is minus 1 times u naught m to the minus 2 power. And then on the right-hand side here, the second term that we're multiplying by, we're taking the derivative of this function in the brackets with respect to x, then what's left over is just negative 0.5 divided by L. Okay? And remember that m was 1 minus 0.5 x divided by L. So we're going to resubstitute that back into the equation. So du dx is minus 1 u naught divided by 1 minus 0.5 x divided by L squared multiplied by negative 0.5 divided by L. So we've just resubstituted in what we know m is. M is that denominator in our velocity function. So we put it back in after we've taken the derivative. And then we can combine the two terms together algebraically. So 0.5 u naught divided by L1 minus 0.5 x divided by L, and all of that quantity is squared. And so this is the change in velocity with respect to position. We found du dx. And now we evaluate it at the point that we're interested in. So at x is 0.25 meters for a length of 0.50 meters. So we know the length of the nozzle, and it's at the middle that we want to evaluate it. We're going to substitute that into the function along with the initial velocity that we have. So the initial velocity, u du dx, so convective acceleration is 0.5 u naught squared divided by 0.5 meters, 1 minus 0.5 times 0.25, which is the distance from the left edge, divided by 0.5. And all of that is cubed. Oh, yeah, because we've got the u term multiplied by the du term. So this is just du dx. And then we multiplied it by u. So that's why it's to the power of 3 in the denominator there. Okay, so in the numerator, u naught squared divided by 0.75 cubed. Like you do all of the combining of terms on the inside of that, then it is 0.75, and the 0.5 in the numerator cancels out with the 0.5 in the denominator. So that is 2.370 u naught squared. And the initial velocity that we were given is that it's 10 meters per second. So if we want to know what is du dx multiplied by the velocity, so that's the definition of convective acceleration, then it's going to be the 10 meters per second squared multiplied by the 2.370. So we just substitute in the initial velocity here to u naught squared. And so that is 237 meters per second squared. So that's how rapidly the fluid is accelerating. Wait a moment for the screen to switch back on. Here at the middle, it's 237 meters per second squared, just based on this function, which is a reflection of the taper angle of the nozzle. So if I remember correctly, you'll need to apply these same ideas on the homework assignment, where you have to know, for instance, that the convective acceleration is the velocity at a certain point multiplied by the velocity gradient, du dx. So you evaluate, find what is the velocity at the location in interest, if you've got an equation defining that and you multiply it, sometimes the velocity gradient is given directly. You don't always have to use the chain rule to define it. Sometimes it's just, they'll tell you directly what is the change in velocity with respect to position. So that's convective acceleration. And just to review some of the definitions of last time, steady flow is when the velocity is constant with respect to time, meaning that there's no local acceleration. Uniform flow is when velocity is constant with respect to position, meaning that there's no convective acceleration. So local and convective, these two different types of acceleration, both cause changes in pressure, and they each have different formulas that are used to calculate the change in pressure. In today's class, we're going to be talking about Euler's equation, which applies local acceleration to a flow field and calculates a change in pressure. And in a future class meeting, we will look at the effects of convective acceleration, which is applied using Bernoulli's equation. In our lab next Tuesday, we'll be using Bernoulli's equation to look at a change in pressure through a contracting nozzle. Just to summarize, steady flow, remember, is when it's constant over time. Unsteady flow is when the flow velocity is changing over time. But in both of these cases, because the pipe walls are parallel, then that means that there's no change in the velocity with respect to position. But you could have a nozzle where you have either the diameter expanding or contracting, and then that would mean that you have non-uniform flow and the flow velocity is changing with respect to position. But there can be both unsteady and non-uniform flow at the same time. If you had unsteady and non-uniform flow, then what that means is that there's an increasing velocity over time in some sort of a flow field that is contracting or expanding, so that the flow velocity is also changing with respect to position. So I wanted to point this out. It's a 2x2 matrix where you can have steady uniform flow, you can have unsteady uniform flow, you could have steady non-uniform, and then most complex of all is when the pressure is changing both because the flow is experiencing convective and local acceleration simultaneously. So Euler's equation is used for local acceleration, and it models the pressure that is experienced by a fluid when it's accelerated over time. And hydrostatic equation already tells us what happens if it's not moving at all. And remember, the formula for the hydrostatic equation is simply that the delta P is delta H times gamma. And there is an acceleration built into the hydrostatic equation. The hydrostatic equation is assuming the gravitational acceleration of g. But what if the tank is accelerating upward so that it's experiencing the effects of gravity and also an additional 9.81 meters per second squared? So think about how would the pressure maybe be increasing as you go down through the fluid if the tank is accelerated up. The change in pressure for each unit of depth would be effectively double then, because there's already the 9.81 meters per second gravitational acceleration. And then if you're accelerating upward at that same rate, then the change in pressure would be the sum of the gravitational effect and the physical acceleration that it's experiencing. Now, I'm a little bit reluctant to even mention that thought to you, that you have to somehow account for gravity and also the acceleration that the tank is undergoing, because you don't need to account for it separately when you use Euler's equation. This is just kind of like a thought experiment to make you comfortable with the idea that this tank of water is going to have even more pressure at the bottom if it's being accelerated up. But if the tank was falling down and it was accelerating downward at g rather than being steady, if it wasn't motionless and if the water was falling downward, then there would be no pressure change through the fluid. For instance, in space where there's no gravity, a tank of water, if you had a pressure transducer, you'd notice no change in pressure as you go up and down through the tank of water in space. Because there's no acceleration, that means that there's no pressure change. So here, gamma, the unit weight of water, is the density of the fluid multiplied by g. So the unit weight of a fluid depends on whatever acceleration it's experiencing. So I guess you could say that in space, water still has a density of 1,000 kilograms per cubic meter, but maybe the argument can be made that it doesn't have a unit weight of 9810 newtons per meter cubed because it's not experiencing any gravitational acceleration when that water's in space. Okay, so origin of Euler's equation is best understood if we consider Newton's second law and the fact that an element of water is being accelerated, the local acceleration, and it's experiencing an acceleration because of an imbalance in forces. That's what causes acceleration, is the fact that the water is being pushed more on the left side perhaps than on the right side. So here, think about if we had a cylinder of water. It's just in a flow field, one of the elements that we could create, like you could define our system as being this cylindrical shape, and because it has mass, if this is on Earth now, let's return back to just normal earthly environment where there is gravitational acceleration. So that means that the weight of the water would be acting downward, and there would be some pressure that's acting on the left side of this cylinder of water, and there would also be pressure acting on the right side of it. It would be different than the pressure acting on the left side because it looks like this is vertically oriented in part, and so the pressure would be less. The delta P could be a reduction in pressure if it is not as deep in the water. So in some direction, in the L direction, if we accelerate this fluid, because it's experiencing a local acceleration, then there's going to be a change in pressure from that as well. So some of the questions we would need to ask to do a force balance is, how much mass does this fluid have? If we're going to do a force balance, then the force that's acting in the L direction, external, would be the pressure that this is experiencing. So pressure times the cross-sectional area. So then that would be a force that's acting in the L direction. And then opposing the movement of this element in the L direction would be whatever pressure is on the front face of the cylinder. And so the pressure that was at the bottom plus the change, which would be a reduction. So P times A is a force that's acting in the opposite direction. So if the force on the back side of the cylinder is greater than the force on the front side, then that cylinder of water is going to be accelerating in the L direction. So the reason why there would be a change in pressure is partly because of the depth, but it's also because of the movement of the fluid. The change in pressure between the 2 points is because the water is accelerating in the L direction. And just think about what happens when an astronaut is launched into space. That's a pretty vivid example of local acceleration. Like they're in the rocket and they're laying so that their heads are up into the sky. They're not like facing forward, and part of the reason for that is because there's so much force, they want to spread out the force over a big area of the astronaut's body. So it's spread out over their back, and their head is resting against a seat, and their legs are presumably being supported as well. Because when they're accelerating upwards, they're feeling like their body weight is really heavy, many times the normal force of gravity. So as they accelerate upward, the increased pressure is in the opposite direction. So it's feeling like they're much heavier than they ordinarily are. And the same thing is true of a fluid, that a fluid that's being accelerated in one direction has an increased pressure in the opposite direction that the fluid is being accelerated. And that's what Euler's equation describes. It describes a change in the piezometric pressure with respect to movement in the L direction that's caused by a local acceleration. So over here on the left-hand side, that's saying that the piezometric pressure change in the L direction is the opposite. So the minus sign here is because the pressure increases in the opposite direction of acceleration. So here A sub L means the acceleration in the L direction. It doesn't necessarily have to be like in the horizontal direction or the vertical direction. Sometimes that's what we do, is we apply Euler's equation like right along a well-defined coordinate. But it could be in 3 dimensions. This L direction could have X, Y, and Z components to it. But let's just say if we are thinking in the X direction, if we had some water and it's accelerating forward, then what Euler's equation allows us to do is predict how the pressure plus gamma Z, so this is piezometric pressure inside the brackets here, the sum of those two terms is going to be changing in the distance between 2 points in the X direction. So the fluid is accelerating horizontally, A sub X. The fluid has some density. The fluid has some unit weight. So gamma here depends on G. It depends on the normal Earth's gravitational. The gamma doesn't depend on the acceleration being experienced by the fluid. So you just use the normal unit weight of the fluid inside the parentheses here. And so what this is saying is that the change of the piezometric pressure in the increment between 2 points is negative, so it's increasing in the opposite direction from the acceleration. So there are 2 points some distance apart, delta x apart. So delta x is how far apart location 2 and location 1 are. And according to our standard method of keeping track of the what is considered a positive direction for the acceleration, we have to use kind of like a standard approach of saying that to the right would be positive x. So that, if the fluid particle was moving rightward, then we'd assume a positive acceleration. And in assigning location 2 and location 1, whatever of the 2 points is further to the right would be location 2. And whichever of the 2 points is further to the left would be location 1 in this formula. Because in this formula, one of them is subtracted from the other. And so we can't interchange what is point 1 and what is point 2 if the acceleration has direction, and it does. So just to make this kind of abstract idea a little bit more clear, let's take the example of this truck. Let's just imagine that this truck is a normal box truck that you see all the time, but for whatever reason, it's full of gasoline. So it's carrying gasoline that has a unit weight of 6.60 kilonewtons per cubic meter, and it's slowing down. So right now it's moving to the right, but its velocity is decreasing, so that means that its acceleration is to the left. So the acceleration, when we substitute it into Euler's equation, it's going to be a negative value. A sub x will be negative 3.05 because it's slowing down. Now, this tank, if you look at it, here at location T, it has 0 pressure. Like it could be that it's vented to the atmosphere at this corner here, and so the pressure is 0. But because the tank is slowing down, you can see from the picture that the liquid level is all the way to the top. If it wasn't to the top, as it was slowing down, the liquid would be sloshing forward. Just think about when you hold a glass of water. If you were in a car and you're holding a glass of water and suddenly the car slows down, the water would spill out of your cup forward. But let's say that the car is accelerating forward and you're holding a glass of water. If you accelerate forward, then the water is going to spill onto you. So in this case, the truck is slowing down, so that means that the liquid wants to continue moving forward. And so there's an increase in pressure at A. So there's more pressure at A than there is at T. And then here you can see location B is below location A. So the pressure is going to be bigger at B as well because there's the vertical component of pressure changing. So what we're going to do is take a look at Euler's equation and how it allows us to calculate the magnitude of the pressure both at A and at B with this given pressure here. Location T is 0. Now, if we want to get some of the preliminary stuff out of the way, then our first thing to do is determine the density of this gasoline, because we know the unit weight, but it didn't specifically tell us the density of the fluid, and we have to use both in Euler's equation. The equation has both density and unit weight. So if this formula for density is gamma divided by G, so it's 6,600 newtons per meter cubed divided by 9.81 meters per second squared. It's 672.8 kilograms per cubic meter. So that's the density of this. Our acceleration in the x direction is negative 3.05 meters per second squared. And in the x direction, we assume that x is positive to the right. So since the truck is slowing down, that means its acceleration is to the left, and that's why we have the negative sign there. So Euler's equation here, we can't immediately start substituting in numbers into that form of Euler's equation. We have to expand it out for the 2 points that we're interested in, and also assume a linear variation between 2 points. And so the form of Euler's equation that's on your formula sheet is this first one. But what you have to do is look and see, like, in what direction is the acceleration, and then expand it out to apply to that particular direction. So in x, then Euler's equation, this partial derivative with respect to L, if we assume a linear variation, is just a change in P plus gamma z with respect to some distance between 2 points is the density times the acceleration in x. Between A and T, location A is further to the right. So what I'm going to say is that A is location 2 and T is location 1. Because A is further to the right, then that means by definition it's going to be location 2. When I expand out the formula to look like this, P plus gamma z at location 2 minus P plus gamma z at location 1 is negative delta x density times the acceleration in x. In other words, that's the pressure at location A plus gamma ZA minus the pressure at location T minus gamma ZT is equal to negative delta x times density times the acceleration in x. So this minus distributes through to both terms inside of the equation. So minus P sub t minus gamma ZT. Any questions so far in just this first step of expanding out Euler's equation in the x direction? Now, you can tell just by looking that location T and location A have the same elevation, that their height above the bottom of the truck is the same. So we can say that ZT is equal to ZA. They have the same elevation. So these elevation terms cancel out of Euler's equation. So all that's left is the pressure at A minus the pressure at T is what's on the right-hand side of the equation. And we're trying to find out, in part one here, what's the pressure at point A. So we could say the pressure at A is the pressure at T minus delta X times density times the acceleration in X. So just rearranging this with algebra, moving the pressure at T to the right-hand side of the equation. And now let's substitute in the actual values. We know that the pressure at T is 0, okay, minus delta X. So the distance, the horizontal distance between T and A is 6.1 meters. The density of this gasoline fluid is 672.8 kilograms per cubic meter. And then the acceleration, we have to put the minus sign in here because the acceleration has a direction component to it. Negative 3.05 meters per second squared. All right. So then that makes the pressure at A is 12,517 pascals. Now, any questions so far? Now, instead of just going from T to A, let's apply Euler's equation between location T, where we know the pressure is 0, and location B. And we can do that because there's only acceleration in one direction. It's in the x direction. If this tank was accelerating both to the sideways and vertical, then you can't go directly from one corner to the other. If it was accelerating up and to the side, then we'd have to go from T to A using the horizontal acceleration, and then from A to B using the vertical acceleration. But this is a little bit simpler than that. This is just accelerating in one direction. So, so far, we have found the pressure at A is 12,517 pascals. And now we're going to just see if we can calculate the pressure at B. The pressure at B is going to be more than the pressure at A because it's lower in the fluid. You know, it's beneath A. So it's this pressure effect that was caused by the deceleration. And then on top of that is going to be the pressure increase that comes from being down inside of a fluid. We could call that the hydrostatic effect, except for that this isn't water and it's not static. But still, as you go down through a fluid, if there's no acceleration in the vertical direction, then the pressure is going to increase at the rate described by gamma. Okay, so let's continue this example. On the other whiteboard, let's find out the pressure at location B. Okay, so we're going to go from location T to B. So that means that T is 1 and B is 2. because location B is further to the right. And so here when we expand out Euler's equation, then we're going to have this location B will be what we put in the first term of the left-hand side of the equation. So it's the pressure at B plus gamma ZB minus the pressure at T minus gamma ZT is equal to negative delta X times the pressure times the acceleration in X. So let's assume that the bottom of the tank is our elevation datum. So we're going to say let Z sub B equal to 0. So if that's how we start measuring elevations, the bottom of the tank, then that means Z sub T is 1.83 meters. So Z sub B is going to cancel out. So that means that the pressure at location B is going to be the pressure at location T plus gamma ZT minus delta X times the density times the acceleration in X. Okay, so let's substitute in the values that we know. The pressure at T is 0. That's where it's vented to the atmosphere and there's no pressure there. Plus the unit weight of the fluid, so 6,600 newtons per meter cubed, multiplied by the Z sub T. So that's the elevation at location T above the bottom of the truck, so 1.83 meters, minus the distance between the 2 points, the horizontal distance. And so the delta X is not talking about like what's the straight line distance between the 2 points. It's just what's the horizontal component of their distance. And so delta X is 6.1 meters. Multiplied by the density, which is 672.8 kilograms per cubic meter, multiplied by the acceleration in X, negative 3.05 meters per second squared. So if we find the relative contribution of the pressure increase of these two parts of it, there's 12,078 pascals from the first part, and the second part is 12,517 pascals. So in total, the pressure at B will be 24,595 pascals. And so the pressure increased at B because it's deeper into the fluid, and also because it's further to the right in a fluid that's decelerating. So the pressure increase was in part because the truck is slowing effect. So this part is because the truck is slowing, and this part is because the location is submerged. That's the relative contribution of each of the effects that's contributing to pressure at B. You can think of this as like the hydrostatic part of it. You know, the 12,078 pascals is because the pressure increases as you go down through the fluid. So that's the hydrostatic component. And then the 12,517 that's the part that was caused by the fluid being accelerated to the left. Let's pull up the homework assignment and look at a couple of problems just to try and interpret and apply what we've talked about today to the questions that you need to answer. Problem 4 is so easy. I hope you appreciate how easy that problem is. All right. Problem 5 is a problem where the fluid is accelerating downward at a rate of 12.5 meters per second squared. All right, so we just did Euler's equation in the horizontal direction. So the acceleration was in x in this example. In problem 5, the fluid is moving vertically. So it's in the z direction. So Euler's equation looks a little bit different when you're applying it in the z direction. When you're applying it in the z direction, it is pressure plus gamma z at location 2 minus pressure plus gamma z at location 1 is equal to negative delta z times density times the acceleration in the vertical direction. So the difference here is instead of delta x, when we're applying it vertically, it's delta z. Okay, so that's one thing I wanted to point out. But let's together talk about how we would apply this equation, Euler's equation, to problem 5. So who remembers what the rule is for determining what gets assigned as location 2 versus what gets assigned as location 1? On that last example with the truck, it was whichever point is further to the right is location 2, since the acceleration was horizontal. When it's vertical, what's 2 and what's 1? The point that's higher is 2. So what we would say is it's going to be the pressure at A plus gamma ZA minus the pressure at B minus gamma ZB is equal to delta Z times the density times the acceleration in Z. So Z positive is up. Now, what are we going to do with this where it says, and is accelerating downward at a rate of 12.5 meters per second? Where does that 12.5 go in this formula? Where is it? Yes. So we're going to put the acceleration here. So what number will I put in for the acceleration? Negative 12.5, right. Negative 12.5 because it's accelerating downward. Negative 12.5 meters per second squared. All right, so here we are given the elevations, 35.64, 32.19. So from the given elevations, you can substitute those numbers directly into ZA and ZB. And then the delta Z is obviously just the distance, the vertical distance between these 2 points. So what you're going to be solving for is what is the pressure at location B. That's the unknown. Everything else in this formula you're going to have, it's water, so 1,000 kilograms per cubic meter. It's water, so gamma is 9.81 meters per second squared. The pressure is already given at location A. So you have everything you need in that formula except for the pressure at B, and that's the unknown. All right. Now, problem 6 is a little tricky because this is accelerating both upward and also to the right. So the pressure in the enclosed accelerating tank is 65 kPa at point P. So here's point P. And then 183.6 kilopascals at point C. So we want to find the distance between them. So it's the same basic formula. Let's just, for this next problem, reassign the locations based on what we know. We don't have an A and a B like we did in the other one. So let me erase that. What's location 1? If we're trying to find, this P and Z, and we're accelerating vertically, then what is location 2? It's P, because it's the one that's further up. So it's the pressure at P plus gamma ZP minus the pressure at C minus gamma ZC is equal to minus Z density acceleration Z. Now, the fact that it's accelerating sideways does not change anything about the pressure change between P and C. So the fact that it's accelerating sideways definitely will affect, like, the pressure down here on the right side of it is going to be less than the pressure on the left side because it's accelerating sideways. But that doesn't have anything to do with what problem 6 is asking. It's just, it's accelerating, and we know the pressure here at point P. That's known to be 65 kPa. So we want to know, if you also know the pressure there, so we know the pressure here, we know the pressure there, we know the unit weight of the fluid, the liquid in the tank is water, so we know the unit weight, we know the elevations. No, that's what we don't know, is the elevations. We know the density and the acceleration, so the only unknown is the distances. And so what you'll have to do is you'll have to say, maybe we assume that our datum is the bottom of the tank. So by definition, Z sub C is 0. And so if you say the bottom of the tank is 0, then that just means that Z sub P is basically the distance m. And then also, this delta Z is the distance m. So then there's just the one unknown in the formula, is we're trying to find out how far apart they are, and use Euler's equation to determine it. So you've got these two problems where you're going to have to apply Euler's equation in the vertical direction. Anybody have questions about that?
So the 197 and 3.7 is just extra information?
Yes, that's right.
But say like you had point A on the right side, and you wanted to do the same process.
Yep.
Would you just use the horizontal acceleration?
Yes. Yeah, so that's a great question. What if we know the pressure here on the left side, point P, what if I said, tell me the pressure on the right side? So in that case, then you'd ignore the vertical acceleration, and you just apply the horizontal acceleration to determine the pressure change between the 2 points. And that will be coming up in a future homework assignment, where you have acceleration in 2 directions, and you have to kind of put on the blinders and only look at one of the accelerations at a time. It isn't possible to find a like an average acceleration, like using the square root of the sum of the squares. Sometimes people think that maybe that they would like to try that, but you basically do it in steps. What's even more interesting is, so you just ask, what if A was here? What if you know the pressure at P, and I want to know down at the lower right corner what's the pressure? So then what you do is you first go in one direction and then in the other direction. So So you kind of do it in steps. You'd break the problem up into two segments.
And you would apply the Euler's equation twice?
You'd apply it twice. Yep. You'd find out, horizontally, what's the pressure change from P to the top right corner, and then you'd be using the horizontal acceleration for that. And then once you found the pressure at this top right corner, then you'd use, let's say, if the distance was known, then you'd use the vertical acceleration to find out the change in pressure going downward. Yeah. Well, okay, we finished early for once. That's all I've got for you today. Remember, looking at the future here, the next lecture will be online, but lab that day is in person. And you've got that homework 5, which we just looked at. That is due on Tuesday. Have a nice day.